Angular momentum is the rotational analog of linear momentum, and we see it in action in many phenomena, as we discussed extensively in our previous video. Angular momentum is an important physical quantity because it is a conserved quantity. For a point mass, it is classically defined as the cross product between its position vector with its linear momentum. Now, consider the ultimate point mass, an electron orbiting the nucleus of an atom. Quantum mechanics governs the electron character in this subatomic regime. The classical orbit of an electron around a nucleus, or its orbital angular momentum, can no longer take any continuous values. In fact, quantum mechanics would require its angular momentum to take discrete values. What are these discrete angular momentum values? Can all these angular momentum components be precisely determined? How would Heisenberg uncertainty principle govern these observations? Besides the orbital rotation motion, the electron can also have an intrinsic rotational motion around its axis, as shown. We call the latter spin, and it turns out that this is a purely quantum mechanical concept that has no classical analog. In this video, we shall focus primarily on the orbital angular momentum, but will briefly discuss the spin angular momentum towards the end of the video. First, we derive the basic commutation relations between the different angular momentum components and that of the total angular momentum. We then discuss compatible versus incompatible observables. Second, we introduce the ladder operators and their algebra with the angular momentum operators and their utility in raising and lowering eigenvalues and obtaining eigenstates for the next rung. Third, we show how these angular momentum algebra, or their commutator relations, allows us to derive the angular momentum eigenvalues in a very elegant way. Lastly, we obtain the angular momentum eigenfunctions in spherical coordinates. Before we begin, let's first develop some intuitions from simple arguments. Part 1. Quantum angular momentum. Basic intuition. The orbital angular momentum is classically defined as the cross product between its position vector with its linear momentum. In other words, if we know the electron's position and its momentum, we can determine its angular momentum. However, in quantum mechanics, the position and momentum cannot be precisely determined simultaneously, as required by the Heisenberg uncertainty principle. Let's suppose we can experimentally determine the angular momentum components Lx, Ly, and Lz precisely. In this example, the angular momentum vector points along z. Thus, the particle phase space would be in a restricted phase space confined to the x and y plane, which then implies the position and momentum along z is precisely determined. This is in contradiction with the Heisenberg uncertainty principle. Thus, the Heisenberg uncertainty principle forbids the angular momentum components to be determined simultaneously. In fact, we will show rigorously in the next chapter that no two components of the angular momentum can be determined simultaneously. Now, suppose I have a spinning object. I can tell you the magnitude of its angular momentum without revealing any of the angular momentum components. This is possible because the total angular momentum is characterized by the product of angular frequency omega and moment of inertia. It does not reveal its orientation. In other words, observers can view this spinning object from different angle and decipher that it is spinning with omega. Knowledge of omega tells us nothing about its axis of rotation. Now let's suppose only the magnitude of L is known precisely for our electron. Then the phase space of all possible angular momentum would map out the surface of a sphere as shown. In addition, let's also suppose that Lz can be determined simultaneously in conjunction to the magnitude of L. Then the phase space of all possible angular momentum vector L would trace out a circle as shown. Now, as long as the other two angular momentum components, Lx and Ly, cannot be precisely determined, then the particles are not being restricted to a reduced phase space. This is unless Lz equals to L, which would then force Lx and Ly to be exactly zero, which would defy the Heisenberg uncertainty principle, as previously discussed. Thus, Heisenberg uncertainty principle would require that Lz must always be smaller than L. To sum it up, we argue that the total angular momentum L can be determined simultaneously with one of the angular momentum component, herein denoted as Lz. In addition, the Heisenberg uncertainty principle would require that Lz must always be smaller than L. Furthermore, the electron which is bounded can only admit standing wave solution. Thus, Lz must be quantized. Now consider again that L and Lz are precisely determined, where the sphere depicts the phase space of all possible L. The quantization of Lz would then further limit the 2D phase space for these simultaneous observations to be circular contours as shown. In summary, Lz must be quantized, and that its value can never be larger than L. Part 2. Quantum angular momentum operators and commutators. Classically, the orbital angular momentum is given by the cross product of the position vector of the point particle and its linear momentum. The angular momentum components can be expressed explicitly as follows, in terms of the product of the spatial coordinates and the momentum components. The components in these expressions satisfy a cyclic symmetry in the manner as follows. For example, Lx equals to the product of Ry and Pz minus the product of Rz and Py. The next angular momentum component, Ly, can be obtained by a cyclic permutation of the indices. In other words, the indice xyz is replaced with yzx. In similar fashion, we have the same cyclic permutation for Lz. Thus, all angular momentum components are cyclically symmetric and does not distinguish from one another. The angular momentum component can be written compactly using the so-called Levi-Civita symbol and Einstein notation, which implies summation over repeated indices. In quantum mechanics, we use uppercase to denote that these are observables in their general operator form. The standard prescription is then to replace these position and momentum operators with their respective differential operators, according to our choice of representation. We will revisit this again in the later chapters. Operators of physical observables must be Hermitian. For example, we can easily check that the angular momentum component, Lx, is Hermitian. The algebra is straightforward and makes use of the commutator relation, that position and momentum of different coordinates commutes. Thus, orbital angular momentum operators are indeed Hermitian. Lastly, since position and momentum of different coordinates commutes, the ordering of the position and momentum operators does not matter. We can also define the magnitude square of the total angular momentum L square, given by the sum of the square of all components. Clearly, L square is Hermitian since it is the sum of Hermitian operators. Now we have our Hermitian angular momentum operators, which corresponds to relevant observables of interest. We are ready to ask the questions, which of these observables are compatible and can be precisely measured? Part 3. Simultaneous angular momentum observables. In quantum mechanics, if two observables can be measured simultaneously with infinite precision, the corresponding operators must commute. Check out the following videos in our Basic of Quantum Mechanics playlist on commutators and in the Heisenberg uncertainty principle. In a nutshell, if the observables A and B commutes, then there exists a quantum state that simultaneously diagonalizes these two observables, which implies that their expectation value can be simultaneously measured with precision. We call A and B compatible observables. In other words, subsequent measurements of the observables A and B will not change the eigenstate. On the other hand, if A and B do not commute, then we have incompatible observables, and subsequent measurements will collapse the previous eigenstate onto a different eigenstate as depicted. It is as if there is a quantum demon who will scramble the wave function to make the measurement on B probabilistic again. Remember, quantum mechanics accounts for what happens when you measure a quantum system. Now suppose we make a quantum measurement of the magnitude of the total angular momentum. Classically, the phase space of all possible angular momentum vector would map out the surface of a sphere as shown. Are the angular momentum components Lx, Ly, and Lz compatible observables with L square? The former allows us to determine the orientation of the angular momentum vector, while the latter only tells us its magnitude. In other words, we seek to know if L square commutes with any of the angular momentum components. Since L square is spherically symmetric, we do not expect the commutation to differ for the different component. But first, we need to work out the commutator between different angular momentum components. Let's consider the commutator of Lx and Ly. We insert their expressions in terms of the position and momentum operators. The algebra is straightforward, but it makes use of some basic rules for commutators and the commutation relation between position and momentum. We see that the commutator of Lx and Ly yields us Lz. In other words, they do not commute. In fact, from the math, we see that the reason why the angular momentum components don't commute directly derives from the fact that the position and linear momentum don't commute. Thus, if the different angular momentum commutes, it will contradict the Heisenberg uncertainty principle. Similar commutator relations can be derived for the other pairs of angular momentum components, as shown. Again, we see the cyclic symmetry in these relations, thus allowing us to express the general commutator for the angular momentum components using the Levi-Civita symbol. Okay, so we now know the different angular momentum components do not commute. Now, we are ready to check if L squared commutes with the angular momentum components. Let's consider the commutator of L squared with Lx. We write L squared in terms of the angular momentum component square. We make use of the following commutator identities to express the equation in terms of the standard commutators between angular momentum components we derived earlier. Using the cyclic commutator relation between angular momentum components, we indeed arrived at the result that the commutator of L squared with Lx is 0. In other words, L squared commutes with Lx. Since L squared is spherically symmetric and the angular momentum components respect cyclic symmetry, one can show that the general result that L squared commutes with any of the angular momentum component. Thus, one can devise a compatible measurement of L squared and one of the angular momentum component. It is common convention to designate the measured component to be Lz. Then there exists a quantum state that simultaneously diagonalizes these two observables, and we shall denote their eigenvalues as alpha and beta for now, but will determine their explicit expressions in the next chapter. Now, if we subject the quantum state to a measurement of the Lx and Ly components, the wave function will be scrambled and the measurement outcome is probabilistic again. This is because the different components of angular momentum do not generally commute, thus are incompatible observables. This pretty much sums up the key ideas in this chapter. Part 4. Quantized eigenvalues of angular momentum. Okay, we established that there is a quantum state that simultaneously diagonalizes L squared and Lz. Our goal in this chapter is to determine the eigenvalues alpha and beta. From our discussion in Chapter 1, we know that Lz cannot be equals to L if L is finite. Otherwise, this would force Lx and Ly to be precisely determined, or exactly 0. Certainly, the magnitude of Lz also cannot be larger than the magnitude of the total angular momentum. First, let us introduce the so-called ladder operators, defined in terms of the other two angular momentum components Lx and Ly. L plus is called the raising operator, while L minus is the lowering operator. It will become apparent soon why they are given these names. It is easy to see that the adjoint of the raising operator gives us the lowering operator and vice versa. Thus, ladder operators are not Hermitian and are not physical observables. But these ladder operators prove to be very useful in quantum mechanics. It is straightforward to work out the commutator of these ladder operators with L squared and Lz. We shall leave for you to inspect the algebra on your own, so feel free to pause the video here if you want to make sure of it yourself. Okay, we have the eigenstate that simultaneously diagonalizes the L squared and Lz operators. We also have the commutators for the ladder operators in our toolbox. Now, let's operate the eigenstate with the raising operator, L plus. We have now a new quantum state. Interestingly, this new quantum state is also an eigenstate of the L squared and Lz operators. Let's check. Using the commutators in our toolbox, it is easy to show that it indeed diagonalizes L square, and the eigenvalue is same as before, alpha. We can also show that it also diagonalizes the operator Lz, but this time, the eigenvalue is beta plus h bar instead of beta. Thus, L plus promotes the eigenstate to the next rung in Lz, increasing its eigenvalue by a quanta, but leaving the eigenvalue of L square unchanged. Therefore, we call L plus the raising operator. Naturally, we should expect L minus to do the opposite, and it is called the lowering operator. Indeed, one can show that L minus demotes the eigenstate to the next rung in Lz, decreasing its eigenvalue by a quanta, but leaving the eigenvalue of L square unchanged. Therefore, we call L minus the lowering operator. But wait, didn't we say that the magnitude of the eigenvalue of Lz must always be smaller than the square root of the eigenvalue of L square? This means that there must be a maximum and minimum rung for the latter of the Lz eigenstates. Let us denote these maximum and minimum Lz eigenvalues to be plus L and minus L times h bar. We know that the Lz eigenvalues are quantized by the quanta of h bar. Thus, L must be multiples of half integer for this sequence of rungs to make sense. In other words, L must be either 0, half, 1, 3 halves, and so on. Okay, our goal in this chapter is to derive the eigenvalues of L square and Lz, or alpha and beta respectively. We showed that the eigenvalues for Lz is characterized by two quantum numbers, which we denote as L and M. The eigenvalues for the operator Lz is m times h bar, where m is an integer that runs from minus L to plus L. The quantum number L, on the other hand, is multiple of half integers as shown. This relabeling of the quantum numbers from alpha and beta to L and M is to be consistent with what is commonly used in the literature. Our remaining task then is to work out the eigenvalues of L square or alpha. Before we can work out the eigenvalues for L square, we need the following identities in our toolbox. One can show that the operator L square can be written in terms of the ladder operators and the Lz operators as shown in the green box. The algebra is rather straightforward, so feel free to pause the video if you would like to inspect the math. Let's consider the L square operator acting on the eigenstate corresponding to the uppermost rung of Lz. In other words, m is equals to plus L. Since it is the uppermost rung, the L plus operator must vanish since no eigenstate exists beyond it. We obtain the eigenvalue of L square as highlighted in blue. Going through similar math, but now for the lowest rung of the Lz eigenstates, we arrived at the same eigenvalue for the L square operator. Great! We have derived the eigenvalues of Lz and L square only with the help of the ladder operators. Their eigenvalues are characterized by the quantum numbers L and M. L is known as the azimuthal quantum number, which determines the shape of the orbital. M is the magnetic quantum number, which specifies the orientation of the orbital. We summarize here again the hierarchy of eigenstates. For L equals 0, M can only take the value of 0. For L equals half, M takes the values minus half and plus half. For L equals to 1, M runs from minus 1, 0, and plus 1. You see the pattern. The quantum number M runs from minus L to plus L with increment of 1. However, the story is not yet complete. As we will show in the next chapter, the orbital angular momentum only admits whole integer values for the quantum number L. Persevere with me. This is the last bit and we are almost done. Part 5. Orbital angular momentum eigenfunctions and eigenvalues. In this chapter, our goal is to work out the eigenfunctions in position space. The first step is to write down our angular momentum operators in position representation, and the general prescription is to replace the momentum operator with its differential operator as highlighted in blue. For example, here is the expression for the orbital angular momentum vector in the Cartesian coordinate system. It is given by the cross product between position vector and the gradient operator. However, since we are interested in problem with spherical symmetry, it will be convenient to use the spherical coordinates. The position and gradient vector in spherical coordinates are written as follows. In spherical coordinates, the angular momentum vector takes the form as shown, where theta and phi are the polar and azimuthal coordinates. I also remind you the form of the Laplacian in spherical coordinates, which will come in handy when we want to compute the L-square operator in the next slide. We can rewrite out angular momentum vector to pull out the component Lz as shown. The Lz operator is then simply expressed in terms of the differential of the azimuthal angle. The operator L square can then be obtained through the dot product of the angular momentum vectors as shown. Feel free to pause the video if you would like to inspect the math. Now we have the differential form for the Lz and L square operators. Our next step is to find the eigenfunctions that simultaneously diagonalizes them. We refer you to our video on spherical harmonics in the Schrödinger equation playlist, where we went through the derivations of these eigenfunctions in detail. The eigenfunctions to the differential operator L square is given by the spherical harmonics, herein denoted by y. It consists of the quantum numbers L and m, a complex exponential that depends on the azimuthal angle, and the associated Legendre polynomial, which is a function of the polar angle. The associated Legendre function are polynomial functions defined here in terms of the Legendre polynomial, according to the Rodriguez formula. For the Rodriguez formula to make any sense, L has to be integers and a non-negative number. Thus, we obtain the key result, that the quantum number L must be positive integers. In conjunction to this, the wave function y describes orbital motion, so it must be periodic for every 2 pi rotation. This can only be true if m is an integer. In addition, because of the differentials, the associated Legendre function is well defined and non-zero only when m is between plus and minus L. So we obtain the result of the previous chapter, that the quantum number m runs from minus L to plus L with an incremental step of 1. In summary, we presented the eigenfunctions for the Lz and L square operators. This eigenfunction goes by the name spherical harmonics. We also show the key result, that the quantum number L is a positive integer and that m runs from minus L to plus L with step of 1. Part 6. Spin angular momentum. In this video, we have derived the eigensolutions of the orbital angular momentum in the quantum regime. We showed that the quantum number L must be positive integers, and this requirement can be traced to the fact that the definition of orbital angular momentum has a direct classical analog. However, particles can be imbued with an intrinsic angular momentum that is not related to orbital motion. These quantum angular momentum are called spin. For example, fermions can admit intrinsic spin of half, 3/2, etc. Bosons, on the other hand, allows for integer spins, such as photon with spin 1, Higgs boson with spin 0, and hypothetical elementary particles with larger spin. Spin angular momentum of particles is not classical, cannot be described by the classical relation of r cross p. However, the angular momentum algebra that we derived here still holds. We will discuss spin angular momentum in a future video. For example, how was spins discovered experimentally? How do we understand these intrinsic particle spins? How do we depict the wave functions of electrons and photon spins? See you in the next one.